Okay, let's unpack this, seriously.
Huh.
What if some of the most fundamental ideas we have about how the universe works, things like mass and speed, aren't exactly, well, how we've always understood them? Today, we're doing a deep dive into a research paper that directly challenges some key parts of Einstein's special relativity, especially around the nature of mass and even how light behaves. And it makes some really surprising claims. I mean, just imagine the idea that mass might actually decrease with velocity,
Yeah.
or that particles are like never truly at rest, and maybe even that photons, light particles, could have some kind of intrinsic mass.
It's definitely thought-provoking stuff.
It really is. It's kind of mind-bending right off the bat. Makes you wonder how they even start building a case for something so different.
Exactly. So this deep dive will explore how this paper re-examines this idea of velocity-dependent mass and some other core concepts, too. It really offers a broader perspective, pushing us to think beyond the sort of conventional boundaries and maybe question some assumptions.
Okay, that's a pretty radical place to start. But maybe before we get to the really out there stuff, let's ground ourselves. We've mostly learned that as something speeds up, its mass increases, right? That's sort of special relativity 101.
Right, that's the textbook picture.
But this paper takes aim squarely at that. How does it even begin to challenge something so well accepted?
You're right. That's definitely the common understanding, kind of ingrained in how most of us think about relativity. But what's fascinating here is that the paper argues this whole concept of velocity-dependent mass. It isn't exclusively tied to the Lorentz transformation, the math at the heart of special relativity.
Oh, okay, so it can come from other places.
Yeah, that's the point. It argues you can actually derive similar relationships using other space-time transformations, too. Different ways of describing how space and time coordinates change for moving objects. We're talking Galilean, which is more for everyday speeds, but also others like Voigt, Sellery, Edwards, even things called generalized and symmetric transformations.
I haven't even heard of some of those.
They're less common, but mathematically valid frameworks. And if you connect this to the bigger picture, it suggests maybe the relativity principle itself has a broader application, extending beyond just special relativity.
Right, okay. So here's where it gets really interesting for me. The paper's most, let's say, counterintuitive idea, mass can actually decrease with velocity. My first thought is just, how? How is that even supported? It feels like it just flips everything upside down.
It does feel that way. The idea comes from an alternative way of deriving this velocity-mass relationship. The author basically required that momentum and force stay consistent or invariant under these various space-time transformations we just mentioned.
Okay.
And specifically when looking at the invariance of force, F dp/dt, the rate of change of momentum along the direction of motion, say the x-axis, while the math leads to a specific kind of differential equation. It's a first-order linear non-homogeneous differential equation for those who like the details. And the key thing is this type of equation has, well, two kinds of solutions.
Just kinds of solutions.
Yeah.
Okay, tell me more about that.
So one part of the solution, often called the complementary solution in the math world, is really crucial here. That solution shows that mass is actually inversely proportional to velocity.
Inversely. So
Yeah.
faster means less massive.
Potentially, yes. According to that part of the solution, as velocity goes up, mass could go down. And the paper suggests the exact relationship, the constant involved, depends on things like the particle's composition and maybe even the medium it's moving through, the substratum.
Wow. Okay.
Yep.
Yeah, that's the opposite of what we usually hear.
Exactly. And it's in stark contrast to the other part of the solution for the same differential equation. It's often called the particular solution. And that one leads to the result we're more familiar with, the transverse mass, where mass always increases with velocity.
So the same equation gives both outcomes. How does that work?
Well, the paper proposes a sort of general expression for velocity-dependent mass that actually combines both solutions. So you have terms that make mass increase with velocity and terms that make it decrease. This combined expression then allows for scenarios where mass could go up or down, depending on the specific speed and the constants involved.
Huh. So it's not necessarily always decreasing, but it can decrease under certain conditions.
Precisely. It opens up that possibility. And this, of course, leads straight to the question, okay, what happens at really, really high speeds in this new picture?
Yeah, that's the ultimate question, isn't it? What does this mean for particles zipping around near the speed of light, like in our big accelerators or cosmic rays hitting the atmosphere?
Right. Well, the framework suggests there might be an ultimate maximum possible speed, let's call it c.
Yeah.
And this ultimate speed c could be greater than or maybe equal to the speed of light c that we know.
An ultimate speed limit.
Kind of. And here's the really neat part. This naturally avoids the problem in standard special relativity, where mass becomes infinite as a particle approaches c.
Ah, the infinite mass problem.
Well,
Okay, so how does this framework avoid it?
Instead of going infinite as the particle's speed gets closer and closer to this ultimate speed c, its mass m can actually approach zero.
Zero. The mass disappears.
Approaches zero, yeah. And what's fascinating here is how this could potentially explain things we actually observe. Like neutrinos, we know they travel incredibly close to the speed of light, and they have tiny, almost negligible masses. In this framework, maybe that's because they're so close to that ultimate speed c, their near-zero mass becomes a natural consequence.
Okay, that's an interesting connection. So if mass can approach zero, and there's this ultimate speed, what does all this do to our idea of rest mass? And zero. That always felt like such a solid, fundamental property of a particle.
Good question. Yeah, rest mass feels very fundamental. The author is careful here. They state that the m0 that appears in their derivation isn't quite the same as Einstein's traditional rest mass, which is strictly defined at zero velocity.
Okay, so it's a different m0.
It's redefined. It's presented more as an intrinsic or maybe existential mass. It corresponds to some kind of threshold or critical speed within the particle itself.
Threshold speed within the particle.
Yeah, it's a bit abstract. But a core idea, a postulate in the paper, is that particles are actually never truly at rest. Everything that exists has some non-zero intrinsic motion, and therefore this non-zero intrinsic mass, which itself doesn't change.
Nothing is ever truly still.
According to this idea, no.
Okay.
So the change in mass we observe with velocity, whether increasing or decreasing, is seen as more of an apparent change. It's really a measure of inertia, or the energy associated with its motion relative to us, rather than its fundamental being changing.
Wow.
Yeah.
That's a pretty deep conceptual shift. If nothing's ever truly at rest, what does rest even mean anymore?
Exactly. It forces you to reconsider that foundational concept.
So I have to ask, how does the paper square this with all the experiments that seem to back up Einstein? EMC2, nuclear energy, particle accelerators. They all seem to work pretty well with the idea of rest mass and mass increasing with speed.
That's a critical point. The paper focuses mostly on the theoretical derivation, the mathematical possibilities, and the logical consistency within its own framework. It's essentially suggesting that the experimental results we see could potentially be interpreted differently, or that they might fit within this broader framework as well. It's less about presenting new, conflicting data and more about offering an alternative theoretical lens.
Okay, I see. It's more about the underlying theory than directly challenging specific experimental results at this stage.
Right. It's proposing a different way to connect the dots, theoretically.
Fascinating. Okay, let's broaden out again. What other sort of wider implications or new perspectives does this research offer, beyond just the mass changing differently?
Well, just the fact that, as we discussed, you can get these velocity-dependent mass ideas from various transformations, not just Lorentz, but Galilean, Voigt, etc., and this idea of an inherent or existential mass. That alone kind of challenges the idea that special relativity has the exclusive ownership of this concept. It suggests maybe there's a more general principle at play.
Right, a bigger picture.
Yeah, and there's more. The derivations in the paper also imply something quite radical, that the velocity-dependent mass might actually be different depending on which direction you measure it relative to the motion. So mass along the direction of travel might change differently than mass perpendicular to it. This suggests relativistic mass shouldn't be just a single number, a scalar.
Wait, different masses depending on direction, you mean?
It suggests mass should maybe be treated as a vector quantity.
A vector, like velocity or force. So mass would have directionality. That's wild.
It is a significant conceptual leap, yeah. It implies direction matters, not just speed.
And what about photons? You mentioned earlier the paper talks about intrinsic mass for them too. That flies in the face of everything we learn about light being massless. How does that argument even work?
It does contradict the standard view. The paper's abstract touches on this and also on the possibility of superluminal signaling faster than light communication.
Whoa, okay. Superluminal too.
Yeah, these are definitely some of the more provocative claims. Regarding photons, the argument seems to stem from perceived inconsistencies in how photon momentum is derived and interpreted in standard physics. The author essentially argues that a truly massless particle might be an impossibility, suggesting photons could possess a very tiny but non-zero intrinsic mass.
A tiny mass for light itself.
If true, it would fundamentally change our understanding of electromagnetism, quantum field theory, pretty much everything.
Yeah, no kidding. It really makes you ask, doesn't it?
Yeah.
How would ideas like these reshape our whole picture of the fundamental bits of the universe?
It's a profound question. It challenges us to really scrutinize the building blocks we thought we understood.
Man, this deep dive has thrown up some genuinely mind-bending shifts in perspective.
Yeah.
Seriously. We went from mass always increases with speed to, well, maybe it can decrease, from a fixed rest mass to this intrinsic mass idea, and the notion that maybe nothing is ever really standing still. It's like putting on a completely different pair of glasses to look at the universe.
It really is. And I think this kind of research, even if it challenges established ideas, is so valuable. It reminds us to constantly question assumptions, even fundamental ones. It shows that even concepts we think are completely settled in physics can sometimes be re-examined, understood in potentially profound new ways if we explore alternative frameworks.
Encourages us not to take anything for granted.
Exactly. It pushes for a deeper look beyond just the surface level equations we learn.
So, for everyone listening, what is this new perspective on the nature of mass, velocity, even light itself? What does that mean for your fundamental understanding of reality? How might it inspire you to look at the world around you with, well,